Okay, welcome to Chapter 5. We're dealing with probability. We're dealing with discrete probability distributions. The end of the chapter will be our introduction to binomial probability distributions. They're also discrete, but they're of a particular kind that comes from a fixed probability. First thing that we want to remind ourselves of is the random variable. We're going to refer to the random variable as x, and it's going to represent the quantitative variable, that is a number, that is measured or observed from an experiment or a study. We also want to remind ourselves of the difference between discrete and continuous. This is basically the difference between Chapter 5 and Chapter 6. Chapter 5 is discrete. Chapter 6 is our first look at continuous distributions. So what is the difference? There are different types of quantitative variables called discrete or continuous. Discrete data can take on only particular values in a range, while continuous data can take on any value in that range. So for example, discrete data usually arises from counting, while continuous data comes from measuring. My height isn't a perfect number of feet. It could be measured with more detail. It's in a range, whereas my age might be considered to be discrete, or the number of people in a household. So our next example looks at the result of the 2010 census and the number of people in households. This is discrete. It's discrete because the household values can only take on 1 up through 6 and 7 and more. So there's no way of talking about a half of a person in this context. So for example, this says that 26.7% of households in the United States at the time of the 2010 census had only one person living in them. And similarly, 33.6 for 2 people, and all the way up to 7 or more. So you might look at this and you might say, well, this is an observation. This is taken from asking people how many people live in their house. And in a sense, this is a true discrete probability distribution. There is no underlying probability that different households have different sizes. We simply went out and measured. Now, for a discrete probability distribution, that is, for a discrete probability distribution that is not binomial, the mean is exactly what you'd think. It's simply x times the probability of x and then added up. Remember that capital sigma that looks like the capital sideways M says to add up all those x times p of x. So x, of course, is the random variable. In that first case, x was 1. The probability was 0.267. So we'd multiply those together, then we'd multiply 2 times 0.336. We'd multiply 3 times 0.1518. You get the idea. And continue in that way, and then add them up. We don't add up last because of the order of operations. Now, the mean also tells us our expected value. So if you're asked how many people would you expect to be in a household in the United States at the time of the 2010 census, you'd compute the mean. The standard deviation looks very similar too. It's simply saying to find that difference between each of the x values, each of those random variables, and the mean. Square that just like we did before, multiply that by the probability of that random variable, add all those up, and then take the square root. We have to take the square root to undo that squaring that we did. Now let's take a look at doing this in our calculator. So here's our calculator, and let's go through and compute the mean and the standard deviation for this data. So the first thing we're going to do is go into the Stat menu. We're going to leave Edit selected and press Enter. We're now going to load this data. I've already loaded the household sizes, so 1 through 7. So now I'm going to load the probabilities. So I'm looking at, for household sizes of 1 people, I'm seeing 0.267. I'm going to enter that. Then I see 0.336. Then I see 0.158. Then I see, we're now at 4.137. We're now at 5. I need to enter that. 0.063. I'm using the percentage to make this into a decimal. 6.024. And let's see what it says for 7 or more. 0.014. And I'm going to enter that. I've now loaded that into my calculator. This is the first time we've done this, and this is something that we will do many times. So we just completed that second step where we loaded the x values, the random variables, into L1, and we loaded the probability of each of those random variables into L2. We're now going to go back into the stat menu, and we're going to go over to calculate. And in the calculate menu, we're going to leave 1 variable statistics selected. Notice that that's our first option, and I'm going to press enter. So our first list is L1, so that's the random variables. The frequency is the probability of that random variable occurring. So I arrowed down to get opposite that question. Now I want to get list 2. So look at your calculator and look right above the 2 on your calculator, and in blue you'll see L2. Blue means that I have to press the second key and then 2 to get L2. Then I'm going to enter to calculate, and it tells me everything I could possibly wish to know. The x bar, the mean, is 2.52. The standard deviation is 1.416. Notice that n didn't add up perfectly to 1. In other words, when we added these up, it actually added up to 0.999. But that's good enough. It knew what we were doing. So our first look at using our calculators for a discrete probability distribution. If you're using a TI-83, when you select 1 variable statistics, it will actually appear on your home screen. You'll then enter L1, L2 exactly as we did for the 84, in other words, using second 1 for L1. There's a comma key right above the 7 on your calculator, and then second 2 for L2. The rare event rule in classical statistics is basically an assumption, a philosophical assumption, that if something is very unlikely, that is, if the probability is extremely small, then the event is probably either unimportant or the data that was collected is not correct. In other words, maybe there's something wrong with the data. Now there's 2 ways that an event could be unusual. It could be unusually large, or it could be unusually small. So in the first case, we're going to look at unusually large numbers of results. So if you're looking at x successes among n trials, and the probability of x or more successes is less than 5%, then you can consider x to be an unusually high number of successes. So we're not simply looking at the probability of x. We're looking at random variables that are at least that large. So that large or larger. So we need to add up all of those and compare that to 5%. So another way to think of this is if the probability of at least x successes among n trials is less than 5%, then the event is considered unusual. And again, at least means as large as x or larger. You can think of this as not talking about the exact probability of the random variable x number of successes. You can think of this as being as extreme as x. So if you're looking at a value of x that's large, you have to consider all the values larger than it. Similarly, if you're looking at x successes among n trials, and the probability of x or fewer successes is less than 5%, then you can consider that random variable x to be an unusually low number of successes. So if when you look at a random variable and you say, well, that's a small number of successes, then you need to consider all the random variables smaller than it, and that includes 0. Another way to think of this is if the probability of at most x successes among n trials is less than 5%, then the event is considered unusual. And here the key phrase is at most x successes. So we're basically saying this looks like a small number of successes, but we need to consider not just that particular exact value for x, but everything smaller than it if we want to say that that is an unusually low number of successes. So let's look at an example. Let's compare our family size data and ask the question, is it unusual for a household to have 6 people in the family? Well, when looking back at the household size distribution, we can see that the probability of having 6 people in a family is 2.4%. But we're basically asking the question, is that an unusually large number of people in a family? If so, we have to look at all the families larger. In other words, we have to also include the probability that the family has 7 or more people in it. So when we ask this question, we have to take the probability of having 6 people and add the probability of 7 or more to that. That's still less than 5%, so yes, this is an unusually large size for a family in the United States at the time of the 2010 census. If you did come upon many families that had 6 people in the family, what would you think? There's lots of ways of thinking about this, and the first that I thought of is that according to the census, that is not likely to last for long. That is, it may have had 6 people in it to begin fewer people to begin with, climbed up to 6, and then some of those people will move on. The other way of looking at this, of course, is that family size is largely a function of culture. Having aunts and uncles and parents and other siblings, nieces and nephews living with you is probably more common in some cultures than in other cultures. Similarly, some families are simply very large and their children live with them for a long amount of time. So there's lots of ways of looking at this. It's not necessarily 2 adults and 4 children. It could be 2 siblings and an aunt and their grandparents and maybe a parent. There's lots of ways that this could happen. But if you came across many families like this, I think the simplest explanation would be that it's part of a progression. They are currently have a lot of people in their household that will increase to 6 and then decrease, or it might simply be a cultural attribute. Is it unusual for a household to have 4 people in the family? Well, let's look back at our data. So unusual to have 4 people in the family. Now, I don't have to worry about adding up the probability of having 4 people to 5 to 6 to 7 because I'm already over 5%. So this one's a lot easier simply because I look at 4 and I'm already over 5%. So this is going to be relatively straightforward. Nope, it's not unusual. If you came across a family that had 4 people in it, what would you think? I'd say it's not unusual. The family size probably was lower earlier and then will become lower again. Another thing to point out, there's a lot of ways of having a household with 4 people in it. Again, think back to nieces and nephews, aunts and uncles, parents, grandparents. Lots of ways that a family size can have 4 people in it. So it might be temporal, it might be the fact that there's just many different generations. So our next section is 5.2, and now we're looking at a different kind of discrete probability distribution. We're looking at a binomial probability distribution. We saw a little foreshadowing of this with the orange tree question in the handouts. We're now developing this idea fuller. A binomial probability distribution is different from just a discrete probability distribution where you go out and collect the probability of each one. And that's because the results come from a fixed probability. So 4 things have to happen before you can get a binomial probability distribution. There has to be a fixed number of trials. That's almost certainly n, and that experiment is repeated a specific number of times, n times. Now the reason for this is simple. If you simply allow n to get larger and larger until you get the result you want, or until you get closer to the result you want, you're kind of cheating. You need to fix the number of trials to begin with. The next requirement is that the n trials are independent, which means that what happens in one trial does not influence the outcomes of the other trials. Now, this may seem kind of obvious, the idea that if you perform an experiment, there's really no way that that information should move from one experimental subject to another. But really, this is about randomly selecting the members of the experiment. If you don't randomly select the members that are being observed, that are receiving a study, there is every likelihood that you're going to get a cluster that have similar views, similar genetics, similar histories. So this question is really about choosing the sample well. And in a classical statistics course, we usually get around by simply saying that the selection process was in some way random. The next requirement, the third requirement, is that there's only 2 outcomes, which are called success and failure. And that's the words that are used. There is no value judgment here. It's just whatever you're counting is successes, and whatever the other stuff is failures. Now, the other way of thinking about this is that the probability of a success does not change from trial to trial. In other words, we're not saying this is the probability for a household of 1 person, for a household of 2. We're saying that that probability of success stays the same throughout. So remember that P is the probability of success, Q is the probability of failure. So they're simply the complements. P is the thing we're counting, the probability that it happens, Q is everything else. The binomial formula for probability says that the probability that the random variable is R, so whatever that particular number is the number of ways you can arrange R things among n. And then if we've got R successes, the probability of that happening was p to the rth power, that's the multiplicative rule, and we multiply that by q to whatever's left. N minus R is all the other trials. And then there's a reminder of the formula for combinations, n factorial over r factorial and minus r factorial. Now the r factorial in the denominator simply ensures that order doesn't matter. Remember that C for combination is the same as C for a committee, where order does not matter. Let's begin by talking about how we ask questions involving probability. There's 2 phrases you'll see a lot, at least and at most. So let's talk about those in the context of a sample space of 17. So the number of successes could be between 0 and 17 inclusive. So what does it mean to say at least 11? Well, certainly 11 is included, so at least 11 means that we could be talking about 11, 12, 13, 14, 15, 16, or 17. So at least 11 means 11 or more. At most 10 our next example, is talking about all the values that are no more than 10. So that is at most 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. At least 11, notice, is the complement of at most 10. In other words, together we have all 18 possibilities, 0 through 17. So that helps us when we're asking questions about binomial probability distributions. Let's look at a particular example. It says, when looking at a person's eye color, it turns out that 1% of the population of the world has green eyes. Consider a group of 20 people. So first, what is the random variable? Well, it's the number of people with green eyes. The random variable x is the number of people with green eyes. Let's talk about the conditions for a binomial experiment. It says, is there a fixed number of trials? Yes, indeed. There was a group of 20 people. Is this random? Is this independent? And we don't know. We were never told that the sample is random, and as a result, we don't know anything about independence. So the next one, number 2, that second requirement is somewhat questionable. The third, are there 2 outcomes? Well, we're going to assume that either a person has green eyes or not. So that certainly is binary, one of 2 outcomes. Now, does the probability change from one person to the next? Well, again, that comes down to whether it was a random selection of people in the world. Remember, our 1% is a worldwide statistic. So for this to be valid, we have to have a random selection from that same population. So again, we've probably got some issues here. But let's move on. Find the probability that none have green eyes. Well, let's work through this. That is asking us to find the probability that the random variable, that is the number of people with green eyes, is 0. So that asks us to use the formula. First, the number of ways that that can happen. So that's arranging 0 things among 20. And of course, there's only one way that that can happen, and that is if all 20 people in the sample do not have green eyes. The next part asks us for the probability that no one in the sample has green eyes. And in this sense, it contributes nothing, in the sense that we're multiplying by 1. And in that sense, nothing changes. Remember, anything to the 0 power is 1. So that hasn't changed anything. That hasn't affected our probability. In fact, the only thing that affects our probability is the 20 folks who do not have green eyes. Of course, the complement of 1% is 99%. So all of those folks who do not have green eyes, randomly selecting them among the population of the world, would give us a probability in each trial of 99%. And of course, there's 20 people who do not have green eyes. So this works out to calculating 0.99 to the 20th power. We can do that many ways. We could do that with a standard calculator. So if we did that, 0.99 raised to the 20th power. So we're going to raise that to a power. So let's see, that's how are we going to do that? So it looks like we need the advanced functions, so let's go in and take a look at those. And we want to raise this to a power, so we want it to be raised to the 20th power. So any calculator will tell you that we're talking about approximately 82% of the time. Now let's look at this a different way, and that is using our binomial probability calculator. So remind ourselves that there were 20 trials and that we were interested in R successes. and that the probability of a success in any one trial was 1%. So of course the complement is 99%, and we go through and we can see that this works out to about 82%. Okay, so let's look at the next page and see what we're asked to do here. The probability that 9 have green eyes. Of course, we can do that with our binomial probability calculator. The number of successes now 9. And we can see that that gives us, well, approximately 0%. So let's enter that answer. So here we've got what we're interested in, the probability of exactly 9 people with green eyes. So that tells us that we're interested in arranging 9 things among 20. And that happens, well, quite a few ways. It looks like 167,960 different ways. And then we're interested in computing the probability that those 9 folks do have green eyes. So that is 0.01, that is the probability of having green eyes in any one randomly selected person, raised to the 9th power. And then, of course, next, for the other 11 folks, 0.99, that is the probability of not having green eyes in a single trial for those 11 other folks. And of course, this is where we get something so close to 0 that even those other fairly large numbers can't overwhelm it. So where is this? This is so close to 0. The probability that if we randomly selected 9 people from throughout the world, or excuse me, 20 people from throughout the world, and that 9 of them had green eyes is essentially 0. So our next question is at most 3, and there's lots of ways of looking at this, so let's get started. So at most 3 says that x is less than or equal to 3, so that means x could be 0. That is our random variable, the number of people we're considering successes. Of course, success is just a generic word in that sense. Could be x equals 0, x equals 1, x equals 2, or x equals 3. And if you're thinking we could go in and calculate those 3 different values for x equals 0, for x equals 1, and for x equals 3, you're exactly right. We could go in, calculate each of those values, copy it, and then add those values up. I'm going to show you another way to do this, but of course we'd get this answer. Now let's look at our next probability calculator, and that is the binomial probability distribution that's built into GeoGebra. You've got it embedded, but you can also launch a page in GeoGebra and find it going into View as we have before, and then turning on the probability calculator and turning off the other 2. Once we do that, we're interested in a binomial distribution. We're interested in 20 trials where the probability of success, that is having green eyes in any one trial, is 1%, 0.01. And let's go back and see what this question asked us. It's asking us for at most 3. So 0, 1, 2, or 3. So we can say that, well, that it means at most. So x is less than or equal to 3. Now this is nice because it's done several things for us. It has shown us how this probability distribution looks. So in fact, along the right side here is the entire probability distribution. It's shaded the 4 values that we actually care about, x equals 0, 1, 2, or 3. And it's shown us that that gives us a probability of 1. So exactly what we would have gotten if we'd added up all 4 of those cases separately. This is also giving us the mean and the standard deviation. It's also showing us the histogram and shading the portion of it that we are interested in. So a nice way to get the answer relatively quickly. At most 2 have green eyes. So at most 2, so just like before, we're talking about having 0, 1, or 2. So we could add up those 3, or we could go into our probability distribution calculator and say we want at most 2. So change that to 2, and it looks like we get 99.9%. If we did this 99.9%. The next question, at least 4. So that means 4 or more. So 4, 5, 6, 7, 8, 9, all the way up to 20. And now you can see why our new method of doing this is so nice. Not only do we get a picture, but we can see this very quickly. What was this again? At least 4. At least 4 have green eyes. So at least 4. So that certainly means 4, 5, 6, 7, 8. It's adding up all these probabilities all the way up there to 20. But adding up a bunch of zeros is still pretty darn close to 0. The next question. In Europe, 4 people out of 20 have green eyes. Is this unusual? So we're basically comparing it to our test for what it means to be unusual. So to be unusual, we have to ask if the probability of all the values that are at least as extreme, and that's an interesting way to put it. We'll circle back to that phrase. At least that extreme have a probability of less than 5%. Remember that only 1% of the world's population has green eyes, so the most extreme case here is that all 20 people in our random sample, if indeed it was random, have green eyes. So for us to talk about at least 4, well, that is the at least at that extreme. So 4 folks with green eyes, 5 folks with green eyes, all the way up to 20 folks with green eyes. And we've calculated that probability. That probability is 0%. So we know that it is less than 5%. And notice that we're comparing this to 4 people out of 20. That's the same as 2 out of 10, which is 20%. Clearly more than the 0% that we would expect to find. So is in a world population having at least 4 folks out of the 20 who have green eyes unusual? Absolutely. So would we find that the instance of green eyes in Europe is in fact unusual? Okay, let's look at the next page, and we are asked about children with autism. So it looks like n equals 10. We've got 10 children in our sample, and in general the population that we're talking about has an instance of 1 in 88. So of course the random variable is the number of children with autism. Is this a binomial experiment? There certainly is a fixed number of trials. We're not told that the sample is random, so it may not be independent. There are only 2 outcomes. Either a person is autistic or not. We can assume that. I don't know if I personally agree with that. The probability does not change from one person to the next. And again, that is determined by whether this is truly a random and representative sample. Then the instance of autism in one child does not affect another. So like before, it looks like we've got some issues where we're never told that this group of 10 children was randomly selected, and as a result we have no way of knowing if the probability with one child affects the probability of the next. Let's go through and find some probability, find the probability that none have autism. So just like before, we're going to work through this the arithmetic way. So we're interested in finding the probability that none of these children have autism. So the first part of that, of course, is to find the number of ways that 0 things can be arranged among 10. And of course, that is one way. So that doesn't change any of our probabilities, as does the next term. Anything raised to the 0th power is 1, which tells us that it's not going to affect the probability when multiplied. 1 times anything is itself. So the last step, the complement, the 87 out of 88 children in this population who do not have autism, raised to the 10th power, and if you do that in a calculator, you can see that you get approximately 89.2%. So let's pull up a calculator and let's enter this value. So 87 divided by 88, let's press enter so that we know that it will compute that value. Let's then raise it to the 10th power. So raise that to the 10th power and press enter. And certainly we've found that probability. Okay, so let's look at the question, at least 5 have autism. Of course, at least 5 means that we're talking about 5 or more. So let's go into our application. Our probability of success is 1/88th, so we can enter that. We're talking about a sample size of n, and we're talking about at least 5. So we're talking about 5, 6, 7, 8, 9, or 10. Lots of zeros being added up. That probability that x is at least 5 is 0. So we can do it either way, either by adding up the probability of 5 all the way through the probability of 10, or using our probability distribution calculator. On the next page, we are asked at most 2 have autism. So let's go back in. At most 2 have autism. So we're talking about the probability that 0 have autism, 1 have autism, or 2 have autism. And of course, the main contributor to this probability is that 0 of those children have autism. Suppose 5 children out of 10 had autism. Is that unusual? Of course, 5 out of 10 is 50%. Let's go back to the previous page and look at what we learned there. At least 5, so that is 5, 6, 7, 8, 9, 10. So at least that extreme gave us a probability of 0%. So when we're answering this next question about whether 50% of children had autism, I think we can see that the answer will be that that is unusual. To be unusual, we have to ask if the probability of all the values that are at least that extreme have a probability less than 5%. And remember on that page, the previous page in example E, we were asked for at least 5. So at least that extreme. 5, 6, 7, 8, 9, 10, we got a probability of 0%. So is the probability of being at least that extreme less than 5%? Yes, and that's because autism is relatively rare. So we computed that probability and we got 0, which is less than 5%. So clearly 50% is unusual. The next page asks us to, or actually tells us how to find the mean and standard deviation relatively quickly. The mean is simply n, the number of trials, times p, the probability of success in any single trial. And the standard deviation is n times p times q, and then you take that square root. Let's summarize Chapter 5 with a look at everything that we can learn about the example of green-eyed folks. So the random variable, of course, is the number of people with green eyes. Remember that this may or may not actually be a binomial experiment. We don't know if the sample was random, and therefore we don't know anything about independence between one person to the next. Of course, that also affects whether this is independent or not. So let's make a probability distribution. Let's draw a histogram. So the probability distribution is what you get when you find the probability of each individual event all the way 0 to n. And we've got that probability. It's the right hand here. Oh, we need to enter the information for the green-eyed folks. So that was 20, a sample size of 20, and a probability of having green eyes of 1%. So here is our probability distribution. So let's look at that inside of the workbook. So here it is, and now it's asking us to draw a histogram, and we can do that relatively easily by clicking on it and saying to export that picture, an SVG is a perfect choice. So we can export that picture to our workbook. And we can find the mean, the variance, and the standard deviation using the formula from the previous page. Recall that the mean is simply n times p, the variance is n times p times q, and the standard deviation is the square root of that. So the mean is n times p, or 20%. The variance is n times p times q, and the standard deviation is the square root of n times p times q.